to talk about the electromagnetic signals of neutron star mergers, which are not the gamma ray bursts. So I'll explain in a second what I mean. And this work was done in collaboration with Doron Grossman, who was a student, and David Wonderman, who are students in Jerusalem, and Ole Koborkin, a postdoc in Stockholm, and Stefan Rosburg, who is working also at Stockholm, and Ehud Nakar, who just entered. So we all know that neutron star mergers or neutron star black hole mergers are the prime target for gravitational wave detectors, LIGO and Virgo, and we expect to get them operating in probably 2 or 3 or at most 7 years from now, depending on which detector. And the basic idea is that you get this chirping signal and you try to find this chirping signal. So this is a well-known goal of physics and astrophysics to detect these objects. Now, why do we want electromagnetic signal to accompany GRB, to accompany these gravitational wave signals? Why is it important? So already in 1993, we pointed out with Chris Kochanek that first, it will lead to improve the detectability, because if you have an accompanying signal, you can increase the confidence. And as you know, in this fitting of the light curve here, one has to go to 8, 10, even 20 sigma, depending on the situation. If you have an accompanying signal at the same direction at the same time, you don't need to go to 20 sigma. It's sufficient to go to 15 sigma, and this is a huge difference. To me, it was a great sociological surprise that this idea was completely rejected by the gravitational wave community for at least 10 years now. The tide is over, and they are all talking about we must have we must have an accompanying signal. So it was an interesting sociological situation to see the shift. 2 other things is that it is essential for localization, because we want to know where it happened, and without an electromagnetic signal, we'll have only some 10 or 10 degrees in the sky. We will not know where it was. And finally, we can learn much more physics if we get this extra signal. Now, it is all long suggested that gamma ray bursts can do the job. And especially gamma ray bursts are divided to 2 parts, to 2 kinds, long and short, you all know. And the short are harder, and the long are softer. So it was long ago supposed that suggested that these are 2 populations. One is collapsars, and the other one is mergers. So this is very simple. If we have such a merger, we get a GRB from the merger. Now, there is no proof yet of the merger, but even one of the first GRBs, short GRBs, which was detected already in 2005, was found to be localized in elliptical galaxy. Now, this localization in elliptical galaxy hints that this is not the usual core collapse event that we are associating with long GRBs. And it gives a sort of indirect indication that this idea of mergers is correct. Of course, it's not a proof. I'll come later to the possibility that we have seen a proof a couple of months ago in this last June. Before continuing, I want to mention something that Omer will mention and stress more in his talk, that not all short bursts are short. And it is very important to take this back home and to remember this. What do I mean? We have classification according to some division to 2 seconds. This classification according to 2 seconds was based on the observation of one detector of BATSI. But this classification is detector dependent. It depends on the detector via the spectral band of the detector. And BATSI was relatively hard detector. Fermi is also relatively hard detector. And as I mentioned, short GRBs are hard, so they are more likely to be detected in such a hard detector. Swift is very soft, and Omer will talk more about this, but as you can see here, if you look at Swift, this is the probability that a burst is a genuine short or different or a collapsar. And as you see here, this probability goes down very quickly, and this is 1 second. So at 1 second, you have only about 50% chance that a Swift burst is really genuine short, in a sense that it does not arises from a collapsar. So this has to be taken into account. And I'll demonstrate one thing here, and this is from the work of recent work with David Wonderman. So this is the duration, the time, the delay distribution of short GRBs. What we have done here is we fitted the redshift distribution from Swift short burst, as well as the flux distribution from Fermi and BATSI to a model of a luminosity function and the star formation rate, where we allowed for a time delay between the star formation rate and the gamma ray burst. And we find here that there is a best fit with a delay of about 3 gigayears. This is, you can do a fixed delay or you can do a power law delay, but the typical time scale is 3 gigayears. And so this is the delay time, and this is the rate that we get, a rate of 14 per cubic gigaparsec per year. And this number is without beaming. So the real number should be multiplied by the beaming factor if you need to know what's the real rate of. But this fit included only 10 genuine Swift short GRBs. So these were only bursts which, according to this analysis of Omer, had very high probability for being a genuine short GRBs and not contaminated by these short collapsars, which are a problem. Okay, so this gives us as a rate estimate.
The issue is the rate is pretty independent of the time delay, right?
The rate is pretty independent of the time delay. Yes, yes.
So that it doesn't matter if you have a flat time delay or a power law time delay, you're still saying this is the rate per year that you're expecting, yes?
Yeah, this number is fairly flat, yeah.
Right, so they're pretty independent of each other.
The local rate is independent of
the local rate. You mean the
local rate is independent.
The local rate.
Rate for the gravity wave detector.
Yeah, this is the rate which is relevant for the gravitational wave detector.
And by the way, this rate, it's the same rate for a long time. So since the first detection of short GRBs in 2005, all these papers and that, they all find roughly this rate.
All these papers are all the results which everybody who tried to estimate this number find it within this region. It varies from something like 8 to 14 or something like this. So it's pretty robust from this point of view. But there is one issue which you have to recall here, that the rate depends critically on the assumed lowest luminosity. Because if we assume that there is a tail of very low luminosity mergers, then you can increase the rate as much as you want. And so this is for this factor. So the rate is insensitive, and this number is simply the value of the weakest short GRB which was seen. So this is where we take the cutoff. We don't see anything weaker than that, so that's where we cut. If you cut it below it, it will be larger. And the actual rate depends on poorly constrained beaming, and I don't want to go into it. Now, recently, in 13, this burst took place at this redshift. This was a hard burst, so it is definitely a genuine non-collapsar. And when we added it, it just fits directly, exactly. I mean, it was a nice test. It did not change at all the results that we get. But to stress the fact that there are non-genuine short GRBs or collapsar short GRBs, this result that I've shown before were included only bursts that we consider to be genuine short. If we add now bursts which are not genuinely short, the full sample of short GRBs, we get now two populations. What we have here is we allowed for some bursts to follow the star formation and for some bursts not to follow the star formation. So it was very nice that when we took 10 bursts, we got the result that there was all of them followed the star, all of them had delay. When we add the extra 10 or the extra 9, we find suddenly that about half follow the star formation. This is the fraction of stars that follow the star formation, and so 1 minus this fraction simply has a time delay, and this is the time delay. So this is another indication that this. So this is. We'll hear more about this from Omer, but let me go now to the issue of electromagnetic counterparts. The problem with this short GRBs is that the short GRBs are beamed, and it's not clear what is the chance to see one pointing towards you. If you see one pointing towards you, it's fantastic, but if not, then you miss it. And if you miss it, there will be off an afterglow. You'll still see the afterglow, but this afterglow is too weak. So the afterglow is too weak. We will not be able to use it, and so this is it's not sufficient, and we are stuck that this is not a good enough signal. Okay, but we know that this is from a simulation by Stefan Rosbach, this movie. We know that the merger event ejects between 100 to 1/10 of solar masses, and this has kinetic energy of 10 to the 50 to 10 to the 51 ergs. So apart from the merger itself and the gamma ray burst, which we see, there is a lot of action going on in the system. And this action is from this material, which you see here around. And the question is, what is happening from this? Can we see this material? And what I'm going to talk about, two ways to see this material. The first way, which was suggested by Paczynski and Lee in '97, is a macronova. And the macronova is very simply an analog to a supernova. This material, which has been ejected from the neutron star merger, is composed of a neutron star material, which is very rich in neutrons. It's very neutron rich, and it's radioactive. Unlike regular supernova, in which there is one dominant radioactive component, nickel, here we have a combination of materials, and therefore this combined material will give more or less a parallel decay in their energy output. So after about a fraction of a second, after about this is about 1/10 of a second, this radioactive decay sort of saturates and begin a long power law, which something like T to the minus 1.3 to T to the minus 1.2 decay in the energy output of this material, which is simply heating the surrounding. Now, just like, so you can calculate the total radioactive energy, it's almost 10 to the 50 ergs. So it's a lot of energy available in this radioactive material. 10 to the 51, which I mentioned before, is the kinetic energy, but this is radioactive energy. However, most of this energy is not observed because it is dissipated very early on. And at this stage, very early on, the system is extremely optically thick. So all that is happening is this energy goes to heat the material, accelerate it, and the material is adiabatically cooled and accelerated. And this gives to the ejecta something like 0.05 C velocity, additional velocity on top of the velocity which it had from the dynamics of the merger. So this is the story here. What you see here is pictures of the ejecta at the end of the mergers. This is a mosaic of different simulations. This is 1.1, 1.1, 1.2, 1.2 solar masses. So these systems are symmetric. Along here, 1.4, 1.4, 1.8, 1.8. You see that the resulting ejecta is sort of symmetric. As we deviate from symmetry, we go here to 1.2, 1.8. You see that the lighter neutron star is being torn apart by the larger neutron star, which is more compact and more massive. And you can see this very large tidal tail, which increases in size with, when you increase the mass ratio. This is so this is top view, and this is view from the side of one of the systems. So this is basically what is happening, and what I'm going to do in the rest of the talk, I'm going to be interested just in this matter which is coming out here, not in the matter that goes into the center. This is the velocity distribution of the matter, and we see that typical masses, this is the total mass. The total mass is between 10 to the minus 2, 10 to the minus 1. And typical velocity is of order of 1/10 of the speed of light, depending on the different mergers. And we have added here to the neutron star mergers a few cases of neutron star black hole merger. Now, in a neutron star black hole merger, the situation of asymmetry increases. And this increases because we have now even more asymmetry, so more matter is ejected and faster. So these are these two systems. The canonical case that we are considering, 1.4, 1.4 solar masses, is actually one of the weakest because it is symmetric, and in a symmetric system, smallest amount of matter is ejected. So this is the canonical case, but this, for example, these are the two black hole neutron star mergers. Now, this is a typical light curve that you expect. And let me explain what is happening here. Initially, all the radioactive material that is, all the radioactive energy which is emitted is captured because the system is optically thick. Eventually, after something which is on a time scale of a day or a few days, I'll talk about this time scale in a second, after this time, the system has expanded sufficiently and the outer regions becomes optically thin. We don't want the outer region to become completely optically thin, because if the region which is completely optically thin, the radiation is lost simply as gamma rays. And it will be something which we will not see because most of this radioactive decay decays as gamma rays. What we are interested is in an intermediate region in which the optical depth is larger than unity, but less than C over V. And Udi already mentioned this value of optical depth of C over V in his talk about shock breakout, because it's the same physics. If the optical depth is less than C over V, then the photons have enough time to diffuse out when the system is expanding. So we'll have this two photospheres. There is this diffusion photosphere in which tau equal C over V, and the outer photosphere in which tau equal 1. Tau equal 1, everything is lost, but tau equal C over V, the initial gamma rays are captured, they are degraded to lower energies, and at lower energies, they escape out eventually from the tau equal, actually not 1, but 2/3 photosphere, and they escape from that. So basically, the system that we have is something like this. This is at different moments of time. This is this tau equal C over V photosphere. Early on, this C over V photosphere is very large. Very small amount of material is outside, so you don't see any radiation. Eventually, as the system goes on, this is now in co-moving coordinates. So the system is actually expanding, but in co-moving coordinates, the photosphere move inwards. This diffusion photosphere move inwards, and eventually you see this, everything from here to there, and then eventually you see everything from here to the outside, and so on. And the maximum luminosity is more or less when almost this diffusion photosphere almost goes to zero, and you see basically most of the system. And at that time, the heating rate, the luminosity is given by the heating rate equation that I've shown before. It goes like this: T to the minus 1.3. So the combination of these two effects is something like this. You have a graph which increases initially. It is increasing because more and more volume is observed. You see more and more region of the star can be seen. It peaks when you see practically most of the star. This is where you get the peak. And then it drops down. First, it drops down like T to the minus 1.3. Eventually, it will drop down even faster and die out completely, because eventually, all the photons which are emitted as gamma rays will not be captured at all, and nothing will be converted to optical or infrared region. Okay, so these are the shapes of the envelope, this envelope. By envelope now I mean the matter which have been ejected. This is the shape from how do you look at it from different directions. This is from a recent simulation that we carried out. Actually the system is fairly simple. After some initial rearrangement, the system becomes homologous and expands and so on. A very important development which was in the last year was pointed out by Kaysen. And what Kaysen pointed out is that the opacity is dominated by lanthanides, which are very heavy elements with a lot of electrons. And once you have this system with a lot of electrons, the effective optical depth is huge. And the optical depth was estimated to be of the order of 10 centimeters squared per gram, as compared to 0.4 for Thomson and 0.1 for iron-type elements. Now, this large optical depths have two effects on the system. If you look here, this calculation was done for kappa equals 0.1, and we got a peak at about less than 1 day, at about half a day. But if you have a larger optical depth, this means that the system is more optically thick. And if the system is more optically thick, then the time in which it becomes transparent, and which is the maximal time scale, increases like kappa to the half. The luminosity at this time goes down like kappa to the minus 0.65, because the heating rate goes like T to the minus 1/3, and this is the energy that you see escaping. At the same time, the system becomes much larger, so the effective temperature goes down. Because the system is larger, both the luminosity goes down and the radius goes up, so the effective temperature becomes much smaller. So so when you increase kappa, this makes the event longer, weaker, and redder. And this is a figure of the effective temperature of the photosphere here. Let's skip it. What is most important here is the bolometric light curve that we get now from this more detailed calculation. And now we were trying to take into account different viewing angles, because the system is definitely not spherically symmetric. So different viewing angles will have an effect of order of 2 to 3 on the total luminosity. And what you see here is indeed before, when we used opacity of 0.1, the peak was at about half a day. Now with opacity of kappa equal 10, the peak now is at about 3 to 4 days, depending on the system. In this system, which more mass was ejected, the peak moves to about 7 or 8 days, and so on. And the different curves here reflect different viewing angles when you look at the system from different directions. So there is also effect here in from the different directions. So similar results without taking into account the spherical, the difference in observing angles were obtained more or less, were obtained slightly before us by Kaysen and Barnes, and by Hotsuduka and Shibata in Japan. So these are basically the results, and the temperatures that we expect here are around 3,000 between 2 to 3,000 degrees Kelvin, a fairly low temperature. So the signal that we expect here should be in the infrared, whereas beforehand, we would, with a lower opacity, we would have expected the signal to be in the UV or so on. Okay, an additional component which exists in the system is neutrino-driven winds. If this is the disk is NDAF, which is a neutrino-dominated disk. This is the disk which is formed around the black hole, which is actually, we ignored it in the calculation so far, because this disk was part of the material which is captured. This is now, but matter is escaping from this disk, and it has been estimated that about a comparable amount of matter, maybe slightly less, but comparable, could be escaping as a disk, as a wind from this disk. Now, it is important to realize that this material which is escaping from this disk will have a different initial YE, and therefore different nucleosynthesis history, and different opacity. The effective opacity here should be smaller, so it should give a different peak. And very rough modeling of this emission gives now the light curve of this neutrino-driven wind. It's the same argument, but now we use a different opacity and different masses. This is the nucleosynthesis which we get there, but and this is the light curves that you get in different directions, and you see here that the temperatures are completely different. Now that the temperatures are much higher, so it's in the UV or the infrared, but the time scale is much shorter. This is now 1 day, so the peak here is of this emission is at less than 1 day. Okay, the combined signal should be something like this, very schematically something like this. Initially quick, less than half a day, about a few hours, very hot signal from the neutrino-driven wind. This is followed by a broad and wide infrared signal, which comes after that. And
sorry, that was days.
What?
At 2400K.
What did you say?
Sorry, that was, yes, there you go.
The time scale is a week. The time scale is a week.
Thank you.
So what about detectability of this signal? LIGO will give us a very large error box, about 100 square degrees. The dynamical ejecta infrared signal from 300 megaparsec will give something in the H band of 23.5 to 24.5, maybe -1 magnitude at optimal viewing angle. And this will be on a time scale of a few days. It is impossible with current detectors to cover 100 square degrees in the infrared at this magnitude. It is simply, this is not achievable. There is no telescope that can do this. So if we are just based on the, if we just have to look for the macronova signal, infrared macronova signal, and we don't have any other information, it is hopeless. However, we have this neutrino-driven wind UV blue signal. This is again about this comparable magnitude, but on a time scale of shorter than day. This is now possible to do with various instruments. The best one is actually what is called super hypercam on the Subaru. This have a small field of view, but even with a few hours, it can scan this 100 square degrees, and it can do this job. So the detection strategy should be to use deep search on the optical using something like this, hyper-supercam, and then once we have a localized detection, we can have a deep search in the infrared. Because if this is localized, then we have 1 week with a very small position, a very accurate position, in which we can look very deeply in the infrared. So this is sort of the ideal strategy. Okay, now to detect this without any trigger, it's hopeless. I mean, because if we just see something like this in the sky, to really identify that this was such an event, I don't know any model like this. How much time do I have?
6 minutes. 6 minutes.
6 minutes, okay. Now, I already mentioned this burst, 130603b, at this redshift. Now, HST images, which was taken by Neil Tanvir and collaborators, and were interpreted both by him and by Ido Berger, and they show 1 week after the burst and in the infrared signal. So this is an HST image at the position of the burst. This is optical, this is infrared. In the infrared, there is something, there is nothing in the optical. And so this is the light curve that they are proposing. This is the optical light curve. And this...
Was that extended mission?
What?
Was that extended?
Yeah.
10 days after.
This is 10, now I'm talking about 10 days after the burst. 9 days after the burst. We extended, what do you mean extended? In time or space? There is a point source. There is a point source.
It's not extended.
Yeah, so that's not, that's a
This is a point, there is a point source. There is a point source here.
Yeah, thanks.
And this is from Tanvir's paper, from Neil's paper. So this is the signal that they claim. This is a fit in which they take, just like a supernova, red bump of a supernova, So this is now the extrapolation of the afterglow. And this is a light curve from expected from the infrared light curve expected from a macronova. This light curve was taken from the calculation of Otsuduka et al., but other light curves are comparable. The Kaysen's light curve are comparable. Our light curves are slightly different. I'll mention this in a moment. And then, if you believe this one data point, then you have seen this macronova.
It's an excellent fit. It's an
Excellent fit, yeah.
They have only 3 free parameters and they can fit this one data point excellent.
If you believe it, then this is what you get.
What is the green?
What?
What is the green? B-band.
Oh, yeah, this is the B band showing that you don't see anything in other bands. So what is happening here is that there is a consistency between, Tanaka and Otsuduka and Behrens and Kaysen. So this is nice. But as we pointed out in our paper, both groups overestimate somewhat, factor of 2 to 3, the radioactive decay, energy input. If you take this into account, if you compare it with our calculations are, this is slightly too dim for our calculations by 1 or 2 magnitude. But as Andy Fruchter tells me, if you have a theoretical prediction which is off by 1 or 2 magnitude, then you have done an excellent job. So, so I'm not sure whether this is correct or not. Actually, oops, I'm missing some slides here. Okay, so I will say, I don't have the next slide. I'll say what I don't know what happened here. Okay, so what is the meaning of this? If this is true, if this identification is true, this means that it's fantastic. It means, first, that we have verified finally that neutron star mergers are indeed the sources of short gamma ray burst, or the short gamma ray burst, and this macronova is the signature of a neutron star merger, or the radioactive decay of the neutron star merger. This is very nice. This is a prediction which is almost from 25 years ago, so it's nice that it's confirmed. This is if it is true. Another implication, if this is true, is that if this is correct, the amount of mass which was ejected here, it must have been about almost 0.1 solar masses. To produce this late signal, it's very robust, because this is at least, because if we know the decay rate and we see a signal, the most that you can get is all the energy from this signal which is emitted at that time. Even this is an overestimate, because if you can see all the system is optically thin, and if the system is optically thin, the radiation is escaping as gamma rays. So there must be more material than that. But with 0.1 solar mass, or of the order of 0.1 solar mass, if we take the rate of neutron star mergers that I mentioned before, and we take the amount of R-process material in the galaxy, then we need to have about 10 to the 5 events in the galaxy. 10 to the 5 events in the galaxy translate to a rate over the cosmological timescale, over the Hubble time. 10 to the 5 events in the galaxy translate to a rate of 100 events per cubic megaparsec per year, which is beaming factor of about 10. Sorry, about 100 events per cubic gigaparsec per year. I did all written down on I don't know what happened to the slide, but disappeared. So it's 100 events per cubic gigaparsec per year. If you compare it with the number that I've shown before, this means a beaming factor of 10. Perfectly reasonable with what you can. There is no strong limits from observations of gamma ray burst on this beaming factor. The estimates were about 30. Beaming factor of 10 is acceptable. However, there will be a challenge to produce very early R-process nucleosynthesis, because we see R-process nucleosynthesis. There is a good thing and bad thing. The good thing about R-process nucleosynthesis from neutron star mergers is that if you have a neutron star merger, it's a regular event. You have a neutron star material which is decaying. So you expect a regular pattern. It doesn't depend on whether this explosion was slightly more hotter or slightly cooler. You just throw out material and let this material decay. So you expect regular pattern. And one of the basic features that we see in our process, in heavy R process nucleosynthesis, we see very regular pattern of abundances of different elements, which shows some standard process. By very regular, I mean if you take the sun and you compare it to a star with metallicity 10 to the minus 3 of the sun. If you take two such completely different stars, the ratio between different R process elements is the same. The amount is very different, but the ratio is the same. So this shows that there is something robust in the process, and disintegrating neutron star material is a typical robust process which can make this. However, what is a challenge here is that we see such R process material in very heavy, in very low stars with very low metallicity, which means that some explosions like this took place when the universe was less than giga-year old, and it's not clear how they can fit. Of course, you can. It's not the end of the story, but it's a challenge, somewhat challenge to this, and so this is where we stand here. In the last minute that I don't have, I just want to mention that another signal that could exist here is radio flare. This material, which will expand into the surrounding, will effectively produce something which looks like an afterglow or a supernova remnant, depend how you want to look at it. It will be the interaction of this material with the surrounding ambient medium will produce a long-lasting signal, and this signal will be in the radio around 1 gigahertz, and this will last now for months, not for days, but for months or even years. So an alternative signal that we should expect here is this radio flare, and this radio flare should be detectable, and one can search for it with the EVLA, for example, and in fact, I would even try to search for the current macronova, for the current event, the 16003b, for such a radio signal. It may be there, and I think I should stop here.